Hello, welcome to my second video on deriving the Poisson property mass function from the Poisson process. So the goal is to establish this property mass function. And the basic idea here is that in a small range, say we have a big range here, from 0 to t here. And then in a very small range, say this is one small range, and this is another one. So in any small range, the number of occurrence of a certain event is approximately Bernoulli experiment with a success property P. And also, the occurrence at different ranges are independent. And then the number of occurrence in this large range will follow a Poisson distribution. So let's formally introduce the so-called the Poisson process. Suppose that nt is the integer evaluated random variable denoting the number of arrivals in a time interval from 0 to t. And also let the lambda be the given non-negative number. So a process satisfies the following 5 properties, also called the Poisson postulates, is called the Poisson process, which rate lambda. So what happened here is that suppose that we have a time axis. So we have a time period from 0 to t, and then the nt will denoting the number of variables in this time period. So at the very beginning point, so in this case, there's no arrival at all. So that means that n0 will be equal to 0. Also, we have this so-called the independent increment. So which means that we have a s here, and also we have a, say this length is t. So here is the t plus s. All right, and then this piece is the ns. So from from 0 to s, we observe this many arrivals, and also the number of arrivals that we observe between s, also the t plus s, is given here. So that is this difference. So we claim that the n t plus s minus ns is independent of ns. So that's the independent increments. The third one is the stationary increments. So which means that we have a t here. So let me redraw the picture. So we have this t here. So nt is here. And then we have s is here. And then this piece, this point says t plus s. All right, and then we say that the number of arrivals appear between s and also t plus s, which is this, will have the same distribution as n of t. As you see that the interval width of this interval width is equal to t. Also, the width of this interval also equal to t. So as long as these two intervals have the same width, and then the number of arrivals in these two intervals will have the same distribution. So that's so-called the stationary increments. And if this condition is not true, and then we may have the so-called non-homogeneous Poisson process. The fourth property is that now we focus on a very small time interval. So this is 0, and then this is the delta t. So we focus on the number of variables in this short interval. So we say that n delta t equal to 1, and then this property would be approximately equal to the lambda value and then times the length of this interval. So it will be equal to lambda times delta t. Or we can write the property that n delta t equal to 1 is equal to lambda times delta t and then plus the little o of delta t. And also, in this time interval, there are several possibilities. One is that there's no arrivals at all, or there's only one arrival, or there are at least two arrivals. So we say that the chance that the number of arrivals is at least 2 is little o delta t. So in other words, there's no simultaneous arrivals in this time period. So these 5 properties are so-called the Poisson postulates. So this is the major theorem we are trying to establish in this sequence of videos. So we say that the probability mass function of the random variable nt from the Poisson process is given by the chance that nt equal to lowercase n is equal to e to the negative lambda t and then lambda t to the power of n and then over n factorial. And also we write as nt delta Poisson and then lambda t. So in this case, the mean of nt is equal to lambda times t. We will provide 3 proofs following the 5 Poisson postulates. And the first proof actually derived the property mass function here using the linear differential equation. And the second is an indirect approach, which derived the characteristic function of nt. And then we find out that the nt here, the CF here is equal to the CF of Poisson. And then we conclude that nt must be a Poisson random variable. And the third method is also an indirect approach, which derived the moment general function of nt. And then we find out that this moment general function actually is the same as the moment general function of Poisson. And then we conclude that this nt must be a Poisson random variable as well. Okay, so we show the first proof. So we will use the linear differential equation and also mathematical induction to prove the formula, which is this one. So first we introduce the p sub n t is equal to the chance that nt equal to lowercase n. So this is the property that there are n arrivals by time t. And we will solve the pnt for n value equal to 0 first, and then apply the induction on the value of n, which is at least 1. Okay, so for the case n equal to 0, and then we have this p naught t is equal to the chance that nt equal to 0. So this means that So you will consider an interval from 0 to t, and then also we have a delta t here. So this point will be t plus delta t. And then the chance that p naught of t plus delta t means in this time period there's no arrival at all. So this means from 0 to t there's no arrival. Also between t and also t plus delta t also there's no arrival. So which means the nt equals 0, also nt plus delta t minus nt equals 0 as well. And because these two intervals from 0 to t, also from t to t plus delta t, they don't overlap. So by the second property that we have an independent increment, so this property is written as the property of nt equal to 0 times the property that nt plus delta t minus nt equals 0. Okay, so then the first part is just p naught t. And the second part, and now we use the stationary increments, so that's equal to the chance that n delta t equals 0. All right, and now we can add in the property d and c, and then we find out that this chance is just equal to 1 minus lambda delta t, and then plus this little o delta t. Okay, so now we can use the this term and then subtract p naught t, and then divide by the delta t here, and then we allow this delta t equal to 0, and then we find out that this limit is equal to negative lambda times p naught t. All right, and then we can solve this linear. Actually, we just solve this differential equation. So we conclude that the p0 t is equal to constant a times e to the negative lambda t. And also remember that the p naught 0 is equal to the property that n0 equal to 0. And because the initial condition that this property is equal to 1, so we conclude that this a equal to 1. And then the p naught t is equal to e to the negative lambda t, which is here, by plugging this a equal to 1. So we can rewrite this expression as e to the lambda t, and then lambda t to the power of 0, and then over 0 factorial. So now we just finished the first step in the mathematical induction. So now we consider the general case that n is bigger than or equal to 1. So by induction, we are assuming that the p sub n-1 is equal to e to the negative lambda t, and then lambda t to the power of n-1, and then over n-1 factorial. Okay, so now we can draw the picture again. So this is the 0, and this is t, and this is delta t plus t. So we consider the property that Pn of t plus delta t. So this means that in this time interval, there's no arrivals at all. Sorry, there are n arrivals. So this event can be decomposed as 3 cases. The first case is that in this period, there's n arrivals, and then in this time period, there's 0 arrival. So which is the chance that nt equal to n, and then nt plus delta t, and then minus nt equal to 0. So that's the first case. So the second case is that between 0 and t, and then there are n-1 arrival. So n-1 of them. here, and then there must be 1 over here. So the third case is that, say, between 0 to t, and the number of arrivals is less than or equal to n minus 2. And then in this period will be bigger than or equal to 2. Okay, so this is the total property formula. And then we apply the independent increment, and then we write these three properties as follows. The property of nt equal to n, and then the property that nt plus delta t and the minus nt equals 0. So this will be equal to this property. Okay, so we can rewrite these two properties as this form. So now we apply the stationary increments. So we know that this piece is equal to this piece. Okay, and then we can, similarly, we can derive these equations. And now we can see that this part is just equal to P and T. And then this part become 1 minus lambda times delta t. And then the second part, this portion, is equal to P sub n minus 1t. And then this portion is equal to lambda times delta t. And then the third part is just equal to a little o of delta t. So now we take the difference between Pn t plus delta t and with this Pn t, which is here, and then divide by delta t. And then we conclude that this ratio is equal, this limit is equal to negative lambda and then Pnt and then plus lambda times Pn minus 1 t. So this just means that we talk about the derivative of Pnt is equal to negative lambda Pnt and then plus lambda times Pn sub n minus 1 t. And please remember that the Pn minus 1 t is given here. All right. So now we are trying to solve the differential equation as this. And we can treat this differential equation as a so-called the linear differential equations. In terms of derivative of yt, also yt. Okay, so this means that we have an equation like yt derivative and then plus function at times yt and then equal to bt. So in this case, yt is equal to pnt, and at actually is equal to a constant which is equal to lambda, and the bt is equal to this form. So we call this function, this equation is so-called the linear differential equation. All the solutions of this equation actually are the sum of all solutions of homogeneous equation number 5, which is this one, and then a particular solution of the inhomogeneous equation of this number 4, when this bt different from 0. So which means that any solution of this number 4 can be decomposed as the sum of these two functions. So this y sub ht is the solution of the homogeneous equation, and this y sub pt is a particular solution to the inhomogeneous equation of this number 4. So let's talk about these two cases one by one. So the homogeneous equation is number 4 with bt equal to 0. So by solving this equation, we know that the derivative of the log of yt is just equal to minus a t. And then the solution of this equation is just equal to y sub a. We write this y sub ht and then equal to a times e to the power of integration of from 0 to t and then negative au and then du. And because this at is equal to just lambda, so we plug in this au as just number constant lambda. So we find out that this integration is just equal to this, just equal to a times e to the negative lambda t for constant a. So for a particular solution for the inhomogeneous equation number 4 has the form of this, so which is equal to vt times y sub ht. So we can write this one as the vt times e to the negative lambda t. Basically, we just replace the constant a in yh by a function vt. So this is the variation of parameters method. So now we just plug in this back to this equation number 4. So we have this form. And also you can see the left-hand side is equal to this and then plus vt and then times this. Okay, so because of the number 5, and then we know that this is just equal to the derivative of vt and then times y sub ht. So which is equal to bt. All right, and then we can solve this equation here. So this derivative of vt, which is this one, is just equal to bt over this yht. So which is here. And now we plug in this bt back, so which is equal to whatever this is, and then y sub ht is equal to e to the negative lambda a, e to the negative lambda t. So this is equal to lambda and then times this. So this implies that the vt is just equal to lambda t to the power n and then over n factorial. Okay, so a particular solution for this inhomogeneous equation actually is equal to this form. So which means that the all solutions for the equation number 4 is equal to the solution for homogeneous equation, also one solution for the inhomogeneous equation, which is this form. And also remember that the p sub nt is a property mass function. So the sum of this property mass function must be equal to 1. So if you plug in all of this here, and then we conclude that this number a must be equal to 0. So this term just goes away. So we conclude that the p sub n t is equal to e to the negative lambda t and then lambda t to the power n and over n factorial. This is exactly what we want. So in this video, we have derived the property mass function of random variable coming from the Poisson process. So the property mass function actually is given by this formula. And we will derive this property mass function using the characteristic function in the next video. Thank you for watching.